Our next example is a little bit different. It really pertains to some of the things we've covered previously. It gives us a good example of using calculus in a current problem, especially one with current density. And in this example problem, what's the current through a cylindrical wire of radius r equal to a tenth of a millimeter if the current density in the wire varies with radius, yeah, where J is the current density is equal to this J over R. R is the radius of the wire times R, where the J naught is this parameter, 32,000 amps per meter squared. The usual case with wires, especially thicker wires, is that the current varies over throughout the cross-sectional area, and more typically, one gets actually more current going on the surfaces than down the center usually, and that's kind of what this is supposed to model. Current right down the center, little r is zero, and so there's no current. And as you get toward the edges, well then little r is going to be capital R, and so you get more current flowing there. So I'm going to have to take into account that variability of the current density. We won't do this much, but in this class, but with this example, we'll take a look at how you would handle that. So what I do is looking down on this end of the current, I only want to look at the current that's flowing through this infinitesimal ring of thickness dr and out at radius r. Because that ring all has radius r effectively, and so the current density throughout all of this is J naught capital R over little r. I know that J is equal to I divided by area. Here I don't have all of the current going through this shaded area. I only have part of it, so I'll use di for the I, but it's not all the area either, so I'll just write dA since it's just going through the part of the area that's shaded here. And you can actually compute that. We've done this before. It's simply the circumference, which is 2 pi r, times dr, if this is a little spherical or little circular annular piece of area that's of radius r and thickness dr. I can rearrange this to be dr is equal to j of r. J is effectively all effectively at the same radius, so j of r, and times dr, and then plug in the dr here, and plug in what j is. J is j naught over r, so plug that in. J naught capital R divided into little r, I should say. Here, so substitute that. And then dA is 2 pi r dr. And again, that's only the current going through this little piece out at a distance r from the center. And I need to get all of it, so I need to add up all of these di's through every little ring from little r equal to 0 at the center to little r equal to capital R. And as you know, that's a continuous sum, so there's the sum. I go from r equals 0 to little r equals 0 to little r equal big R of everything on this side, which is here. I've got lots of constants. I can pull out the 2 pi r, or 2 pi. I can pull out the capital R on the bottom, and I can pull out the j naught. Little r, r here gives me little r squared. I can't pull those out because they're on the integration variable. And the limits are from 0 to capital R. So now it just becomes an integral problem. So I integrate r squared dr, and the antiderivative of that is r cubed over 3, and I have to evaluate that from r equal to 0 to little r equal to capital R. And doing that, I get the total current in that form. We're not quite done because I assume they wanted a numerical value. So I've managed to get an equation for it, but now I know that capital R is this and J naught is this. So I put those into our expression. J naught was 32,000 amperes per square meter, and little r was a tenth of a millimeter, and so square that. Multiply all that out. When I did that, I got 6.7 times 10 to the minus 4 amperes, or same thing, 0.67 milliamperes.